This is a demonstration of the single cycle computer IDE, Integrated Development Environment, for a series of sample programs. Clicking on the browser and individual instructions folder, there's bundled instructions, logical instructions here, jump instructions, move to and from data stack memory, etc. So the one I'm going to look at now is the set clear bit invert bit in registers R, and set clear and invert bits in the special function registers, and then an end instruction. So this is the first program. Open it up. It will appear. It has a header, and there's a main label which is address 0 in the program memory, and there are 6 instructions and then the end 7 instruction altogether. The instruction set details the format of these instructions, the parameters, etc. But the first is set a bit in register R, R6, and make it bit 13. And this is what's expected in the output. This is the hex output value. This is bit 13 out of 16 bits that's set or asserted. Then clear, same register, bit 13, so it should go back to 0 again. Registers by default are always 0 at the start of a program run. And then invert bit 3 of register 6. So it was 0, now make it a 1. Then do the same for special function register 5 and 4. Set bit 2, clear bit 2, and then invert bit 15. It happens that special register function 5 and 4 connect on the IDE to LEDs and 7-segment displays, and then the end program repeats forever. So having said that, to compile or assemble the program, click on this. If something is typed wrong, for example set ABR, and I compile, it will tell me there's a problem. So check the syntax of the instructions and change those. Assemble. This becomes active, and this is the widget to write instructions to program memory. This is program memory from address 0 up to address 6, 7 instructions altogether. They have a unique address in instruction memory. These are the codes, or the instruction code, which can be seen over on this side of the window. 7 bits opcode, and then there are 9 other bits that are used for different parameters, as will be seen. So I'm going to focus on this IDE first of all. I can single step a program by clicking on this button, and the blue bar will move down to the current instruction. I have some inputs for switches, 7-segment display, LED outputs. This is the register bank, register 7 to register 0. This is the special function register bank, 15 down to 8 and 7 to 0. But 0 is on the right hand side. This is a small window into the data and stack memory. Data and stack memory is here seen. This is the structure of the architecture of the processor. The LEDs are active based on the first instruction in the program memory. So the picture on the right hand side takes on the signal levels within the processor. Not just registers and memory can be seen, but the actual physical signals that are relevant. And it's a subset of the functionality of the whole processor that's shown on the right hand side that's specific to set bit in register R. There's an operand fetch block, there's a function execution unit block, and then there are the register bank to be written to and special function registers which aren't being written to in this particular set bit in register R. There's feedback from the registers right back up through the operand, and it's selecting register R up through this operand, and a star indicates the index of the register that's been changed. Because I'm looking at register 6. Register 6 happens to be both the source and the destination register for set BR is the register number that's there. So R out is the register index for the register that is being written, and also the star here shows that when the clock is toggled, the instruction is executed, this entry here, R6, will change. R6 is also up here. Register write is asserted because on the next clock edge, a write will occur to this register. And the source register is also register 6, and you can see the association in the colours in this field. And the index of the bit is 1101, which is D, which is 13. And that 13 goes into the function execution unit, a component within that, one of many components. It creates a mask with bit 13 asserted. 2000 is bit 13 asserted, and it takes the selected register value, which is currently 0, which is register 6, and it ORs that with the mask. The output of the function unit is there for 2000, and that will be written down to here. Meanwhile, the program counter currently is pointing to instruction 0. The program counter is incrementing the next count value to 1, which on the clock toggle will push through the register and be registered, and change the pointer to memory address, instruction memory address 1, and it will progress through to the next instruction. So this transfers the contents of register RIA, which is register 6, to the destination register ROUT, which is also register 6, with set clear invert check bit index 3 bit set to 1. That's this bit 13. This is an example of an instruction, which happens to be the one that's over here. And it copies R6 to R6. The source and the destination are the same, with bit 13 equals 1. And it also increments the program counter. These are the signals inside the processor. This is a parameter instruction, so is that. But this signal, and this signal are asserted by the instruction decoder, and they control the data path, the flow of data from registers through the operand fetch, through the function execution unit, back to registers again. There is interaction with data in stack memory. Those examples will be seen later in multipliers and other functions within the processor, but this is what's relevant here. So if I single step, then register 6, bit 13 will have been inserted. I will quickly go through the rest of the program, and you'll see this is now clear bit. So the picture has now changed. The behavior of this processor has changed, and the picture reflects that. I won't look at the detail here at the moment, but here I'm clearing the bit 13 in the register, a single step again. This will go to 0, as it does over here. I'm now going to invert the bit, and again there's a different picture over here. This is the invert bit picture, and I can assert, or I can single step the processor, and this will then move to set B SFR, which sets bit 2 in SFR5. SFR5 is 0, 1, 2, 3, 4, 5. But that can be seen over here now. The red indicates the destination register bank. SFR5 is the destination. Here is the address of SFR5. There are 16 of them, so there are 4 bits of an address. Again, the source and destination addresses are 4 bits in the instruction field. The opcode is different again. There's an unused bit in the instruction. And this is a hex number. The value is 2. This is the index, which creates a mask to the 3rd bit. And I am ORing that 0 selected value from SFR6 through the operand. There are 16 possible paths through the operand fetch, indexed by the source address, which is register 5, SFR5. The value is 0, and it's ORed with 4. The output is 4, and that will be written to register 5 if I step again. See this changing over here. The value is 4. Bit 2 is asserted, and you'll see it having changed over here. I'm then going to clear that bit by stepping again. And then the last is invert the bit, so it will again assert that bit here. But this is bit 15 I'm asserting now, which is the upper bit. And the end instruction, notice the diagram on the right hand side. There is no activity. I left the register values here. There's no red box around these. There's no register being written to. There's no activity of register or memory coming through the data path to be processed in here, logical bit operation, or later you'll see your arithmetic, etc. operations. And the opcode identifier here happens to be 0 for end instruction. These are all unused, so it looks like it's doing nothing, but the instruction 0 has a very important meaning. Only one signal in the system is asserted out of the instruction decoder, and that's end program. And notice that this is now changed, because what this is doing is it's taking the current count from the program counter and it's maintaining that. It's selecting the counter next state decode path to maintain that value. So no matter how many times I step or run the program, you'll see I've executed 6 instructions. It will always continue to execute that instruction. It will never progress further. Otherwise you're executing instructions memory has not been defined. So I can single step, and you'll see the instruction execution will increment to 7, 8, etc. And I could also run, and what this does is runs the clock at speed. And we see windows into the remote FPGA, and you can see tens of millions of clock events have happened. And I can pause that and stop it again. Now, if you were watching this side, you would have seen that when I wrote to special function register 4 and 5, that the LED and the 7-segment displays will have changed as well. In this particular case, 8000 to special function register 4 is mirrored on the 7-segment display. Special function 5 would be mirrored to these bits if I was looking at them back then. These are flags, which will be seen in later instruction examples as well. But this gives a sense of the behaviour of the IDE